In this presentation, we'll be talking about the structure of the atom. This presentation is broken up into two parts. In this first part, we'll be talking specifically about the continuous spectrum, line emission spectrum, and introducing energy levels in atoms. Solids, liquids, and gases consist of vibrating particles. These particles are always vibrating because they always have some sort of energy. It's not until you get to 0 degrees Kelvin where there's very, very little vibration of the particles. The vibration of the particles is also related to the temperature of the material. So as the temperature increases, the energy of the particles also increases. There's a diagram here of the spectrum of light surrounding visible light, which is the black band. And this is what we're going to be looking at. In addition to atoms moving around atomic bonds, other particles that can move in a material include protons and electrons. So these could be vibrating in a direction that's up and down, left and right, or any other direction in the material. Now, as there's so many atoms moving in all different directions, there's a wide range of frequencies of electromagnetic radiation that are produced. Now, the continuous spectrum that is produced is independent of the material, and the range and intensity of the radiation only depends on the temperature of the material. So, for example, at room temperature, the radiation produced by the material is low and actually falls into the infrared frequency range. So cats can actually detect this range, and night vision equipment uses infrared to see better at night. The graphs on this slide indicate the intensity of light produced based on the temperature of the material. Although the material isn't named, we can see that in the low temperature range for this particular material, looking at the graph on the left, that when the material is 1700 degrees Celsius, a lot of the light produced is in the infrared range. When we look at the graph on the right, which is just an enlarged scale, we can see that as the temperature increases, a lot of the light is actually in the visible range, being a range of high energies. And if we kept going, we might even get the ultraviolet range. Let's have a look at an example of a globe. So what we've got is a thin tungsten wire that has a current running through it. This current just allows the wire to heat up to high temperatures. The wire is located in an argon gas environment. This is a non-reactive gas, and it just prevents the wire from undergoing combustion. So as the wire heats up, the particles vibrate more, and the frequency of the vibration moves from infrared to the visible spectrum. So it moves up that graph that we saw before. So if we have a look down here at 1000 degrees, we get a very red color. So we're in the visible spectrum in red at that temperature. As the wire heats up further and further, you can see the spectrum move down the line. So now we've got more of an orange color. But as we keep going, say at 4000 degrees, we get to blue, but we don't see the light globe as a blue color. We see it as red, orange, yellow, green, and blue. When you mix them together, our eyes perceive that as a white light. When vapors of elements are heated up, colors are produced. And this color is specific to that element, and we call this the emission spectrum of the element. When we look at neon signs, for example, neon is actually an element, and when this is heated up, it actually produces an orange light. Helium produces yellow, and mercury produces blue. So when we talk about neon lights, it's very specific to the color orange. However, in general language, we apply it to all lights. The diagram at the bottom of this page shows the line emission of a sodium gas, and it's got two line emissions in the visible range of light, being in the yellow region. This only occurs when sodium is in its gas form, not its solid form. In its solid form, when sodium is heated, you get a continuous spectrum, but in this gas form, you just get two specific line emissions. When we look at the example of sodium gas, we see that when it's heated, it's of a yellow color. Now, when we pass this through diffraction grating, we can actually determine what frequencies of light are being emitted by the gas. And by doing this, we can see there's two very specific and distinct frequencies in the visible range. So we don't see a continuous spectrum of light. There's a very distinct number of frequencies in the visible range. So what we can determine from this is that these frequencies are a property of the atom, not due to the vibration of the charges themselves. Let's look at this with a diagram to assist our explanation. So when we shine the sodium vapor light through a diffraction grating, we can separate the frequencies and determine the exact value of the frequencies of light that are emitted by the sodium vapor when it's heated. So by knowing the angular separation from the center point to the first order maximums, we can use this formula here to determine the exact frequency or the exact wavelength of light. So although the human eye can only observe light in the visible range, emissions in the infrared and ultraviolet region also occur. The line emission spectrum of an element is due to the movement of electrons between different energy levels in the atom. In chemistry, we call these energy levels electron shells. Now, a line emission spectrum of a specific element is unique and is different to the line emission spectrum of another element. The diagram that we've got here on our slide represents the different levels an electron could reside. Electron wants to be in its lowest energy state, which is usually closer to the nucleus, so it's closer in the smaller circle. Now, when it's in an excited state, it wants to drop down to a more stable state, and in doing so, a photon is released. So, in this example that we've got, if an electron was in an excited state and it wanted to drop down to the more stable state, which is just circled in red, it's got, for example, in this state, 4 options to do so. 1, 2, 3, 4. And these correspond to very distinct energy levels, and when the photon is released, very distinct frequencies. Let's look at an energy level diagram to help us describe this. So this one here is for hydrogen. So level E1 is what we call the ground state, and it's the most stable state of where an electron would be. So in this, for hydrogen, corresponds to 13.6 electron volts. Now we've got a negative there because the electron is bound to that energy level. We can see that the next excited state for hydrogen is level E2, and it's quite a lot higher. These energy levels are not evenly spaced and are actually related to the nuclear charge. You can see as we progress further from the nucleus, the energy levels get closer and closer together, and there's actually an infinite number of energy levels. When we get to this level 0, which is 13.6 electron volts above the ground state, the electron is actually free and it's not bound to the atom anymore. Electrons want to be in their ground state as it is the most stable state. If an electron is in an excited state, for example, and this one in excited state level 2, it will want to drop down to the ground state. Now in doing so, there's a photon emitted, and this photon corresponds to the difference in energy levels, and in this example it will be 10.2 electron volts. Now this photon of energy of 10.2 electron volts corresponds to a certain wavelength or frequency, and this is what gives possibly the color in the visible range or a specific frequency in the ultraviolet or the infrared range. Now electrons can be promoted to higher energy levels in 3 different ways. If the material itself is heated, the atoms contain a certain energy and can promote an electron to another level. If electrons are bombarded to the atom and electron to electron collisions occur, the electron can be promoted to another level. And the third way is if photons of a certain energy collide with an electron, they can be promoted. Now by knowing the energy difference between 2 levels, we can determine the change in energy of an electron, and as a result we can determine the energy of the photon that's produced, and using this equation, the wavelength of that photon.